Okay. Good evening, everybody, or afternoon, or whatever it is. That's okay. No worries, Lillian. I'll just pop the, so I've got to pop in to the chat today's tutorial, but also next week's, because as it happens, hang on, let me just do the first one first so that I don't get myself confused. Okay, so that's today's, that's respiratory and gas exchange. And I've also got to give you next week's, because even though we have 10 weeks of subject, we only have 9 tutorials. So next week's tutorial is technically independent learning. So you get that, and you get to go through all that by yourselves. Isn't that exciting? Having said that, if you make use of the discussion boards and ask any questions about anything that you're uncertain of, obviously. Because it's the immune system, and God knows it's not as simple as all that. So you might have a few questions floating around in your head about basophils and eosinophils and neutrophils and natural killer cells and blah, 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 all the everything. There's a lot of everything. Okay. However, how are we all? Are we all, the week treated you okay so far? Yeah? No one's in terrible tragedy? Well, you wouldn't. If you were, you wouldn't be at a tutorial, would you? So silly question, Kath. Okay, so nearly there, light at the end of the tunnel. I mean, of course, not really, because you've then got to do 175 after this. But anyway, first half down and kicked, and we will get started. Gosh, Kath's been teaching a lot today. We will get started with the current tutorial and see where our heads are at with this whole respiratory section. Maybe we won't start on the last slide, though. We might start on the first one. Wacky. And still people coming in. Okay. All righty. So we ready to launch? Everyone's happy to go? Yep. Good. All right. Let's start off with our multiple choices, and I'm hoping that these are easy. They usually are for you guys. You never seem to be terribly challenged by anything, which is good. Happy. Okay, so trying to think back to our left and right sides of the heart and what goes where. Which of the following blood vessels does not return blood to the right atrium of the heart? So I think that the answer to this question is figure out which vessel does return blood to the right atrium, and then figure out which one doesn't.
Is it A?
Is it A? So which of the following vessels does not return blood to the right atrium of the heart? Yep, what goes into the right atrium of the heart?
Inferior vena cava and superior vena cava.
Yep, that's right. Exactly. Good.
I don't know about coronary sinus though. Okay.
Well, the coronary sinus is literally just the name for the area where all the vessels come in and out. So it's kind of a bit of a red herring. Okay. So yes, so pulmonary vein is correct. So number 2, moving on it, the trachea on our little laddie over there is which label?
B. Label I mean, like.
B, I. Yes, they're very similar. I know it's quite hard to get those. Those are very easy to mix up. Bruce or Iuse, it's I get that all the time. But yes, that would be our label I. What's the giveaway? I mean, it's a nice picture. It kind of gives it to you. If you look at definition.
Got the coils. It's got the coils, the cartilage-looking coils.
Good. Yes, and not even cartilage looking, but cartilage actually.
Oh,
so yes. Yes, it does have the coils. The cartilaginous rings, if we were going to get all examine about it. Yeah, but that's right. Good, excellent. Moving on. Okay. So this one's a little bit, figuring out what have we learned about pulmonary ventilation. Which two variables actually dictate the mechanics of breathing?
Is it B?
It is B. Does everyone else agree with that? Pressure and volume? Good. It's a little bit of there's a few red herrings in there because temperature does actually come into it in a way, but it's not, it doesn't dictate it. It literally, it may adjust it slightly. Okay. Exchange of O2 and CO2 through the respiratory membrane occurs by what?
Simple diffusion.
Thank you. And yes, absolutely. And this is the great thing about the whole respiratory system is you don't actually have to get too nutty about it because the vast majority of the important stuff is very simple, actually. Yep, simple diffusion from an area of high concentration to an area of low concentration. It's really quite basic and simple. And we all, more about the respiratory system than you think. It should be pretty easy. That we take in O2 and that we breathe out CO2 and that happens somewhere near the alveoli. All you've got to figure out really is what's going on with capillaries and things down at that end, and you've pretty much got it sorted. Oh, that and atmospheric pressure. But that's, yep. All right, we'll get there. Okay, this should be fairly simple, I should think. Oxygen is primarily transported in the blood as which one of those?
B.
Yes, absolutely. Oxyhemoglobin. Somebody give me a quick rundown of what is oxyhemoglobin? What the hell is that word and what am I talking about?
So when the oxygen hangs onto the hemoglobin and travels around. Is that what you mean?
Yeah. Absolutely. Yep. Just remembering that there's hemoglobin molecules within your blood and there's millions and millions and millions of them. They've got 4 particular sites, 4 iron-rich sites that can take up to 4 oxygen molecules. Sorry, apparently English is just escaping me this evening at any given time. Doesn't always take the full 4, but most of the time it will. Okay. And as usual, the Monday tutorial group has smashed through the multiple choice 5 on 5. Nicely done. Okay. Now, this is a little bit more complicated. So now we're not just talking about oxygen and carbon dioxide because this is list 4 ways a molecule. So it could be oxygen and it could be carbon dioxide, but it could be any other molecule as well. 4 ways a molecule can cross a capillary wall. And of course, actually one of our multiple choice questions kind of gave that away. So if you went backwards and have a look at all the different answers that were given for the last question, then you've got your list. It's right there. Yeah. So what are some of the other things on that list? So any molecule. So we've got, you could name the one we just talked about. You could say simple diffusion. What's its brother in crime? So simple diffusion. What's the other one? Facilitated. Yep. And what does facilitated diffusion mean? Facilitated by whom or what? It's all right. I've got all night.
Osmosis.
Sorry?
Is it osmosis?
Osmosis is one of them, yep. But facilitated diffusion, generally, we're talking about protein channels that are embedded in the actual membrane. What's another one? So we've got osmosis, we've got facilitated diffusion, simple diffusion, and there's another one.
Is there like endocytosis?
Endocytosis. Yep, absolutely. Yep, exactly. So that's list. Beautiful. 4 ways a molecule can and does cross a capillary wall. Depends on the size, depends on the charge, depends on all sorts of things. But yep, there's plenty of small molecules and big molecules that need to move across. So we need to know that. All righty. And there we go. Fusion, facilitated fusion, osmosis. Oh, filtration was the other one we didn't land on. Okay, so that's through those fenestrated capillaries. Yep, our little holy fellas. Yep, filtration. Okay, now get myself organised. All right, who wants to give this one a whirl? Defining anatomical dead space. Someone can look it up or look at their notes. I'm sure that you've got notes on this.
I'm just trying to remember off the top of my head, so I'm probably wrong, but I'm trying to challenge myself.
No. This is good. It's good.
So for me, what I understood from it, so it's meaning like the spaces where the oxygen doesn't actually adhere to anything. Is that right or no?
Yeah, no, sort of. You're on the right track. Yeah. So it's actually, before I answer, I'm going to get somebody else to give me what they think. Just imagine it's a debating team, and so you got that. It's where oxygen doesn't do anything. Who else has got some idea of anatomical dead space?
It's the air that's not used for gas exchange, so like the leftover air.
Yep, absolutely. So it's a very simple idea, actually. It's simple. We breathe in, we breathe out, but we don't breathe everything in and we don't breathe everything out. And there's some air that doesn't participate in the gas exchange. And literally this is the same reason. So again, I'd love to have you guys in a lab, because anatomical dead space, oh, you can do this, you go to the butcher, is the reason why if you go buy like a sheep's pluck of lungs and you put them in a bucket of water, like dead sheep lungs, they will still float. Right? There is still a whole heap of air in those lungs, in all the alveoli. It's not participating in gas exchange, it's not doing anything, but there is still, does anyone know off the top of their heads what the amount of air is approximately, that it is anatomical dead space?
At 150 mil?
150 mil. Yep, it's not much. It's only small, but that is anatomical dead space. Good, spot on. That's exactly the definition, because there you go. Total volume in all of the airways where air is exhaled, but it's not changed. So it doesn't participate in gas exchange. Spot on. Excellent. All right. Moving right along. Okay. Now, this is an interesting one to do as a distance tutorial because it specifically says color stuff in and label it. Now, we're not going to be able to do that right now. However, let's do a descriptive journey, for want of a better term. So if you had to identify the alveolar epithelium, which bit of the picture would you choose?
B.
Yep, absolutely. And maybe the top square thing up there as well, just saying it's what we're talking about is the covering, the coating of the alveoli on the inside. So the epithelium, yeah, and you'd colour that B. All right, what about the capillary endothelium?
C.
Yep, and then maybe you want to go up into the very, very top one and do all the little capillaries as well, if you feel like it. But that would be a bit of overkill. Okay, where's our red blood cells? Where do you think they are?
C.
Yeah, yep, they're absolutely down there. The alveolar chamber, well, oh, I just realized that I've highlighted the word red in pale blue. It's challenging. Okay, let's just jump because it's really hard. I'm just going to go to, all right, let's go down to the meat and gravy of this. Adding symbols for O2 and CO2 in the sites where they'd be in highest concentration. And then the arrows down the bottom there in C obviously are indicating O2 and CO2. So where is oxygen in highest concentration with the alveoli, and where is O2, the other one, carbon dioxide in highest concentration? Where do you think? This is quite logical if you think about it.
So oxygen in the alveoli and carbon dioxide in the capillary?
Yep, absolutely. Because that's logical, right? Yes? Yeah. Okay, cool. All right. So from that should be reasonably easy to figure out in which direction things are going. And also just from your general knowledge of living as a human adult, obviously, yeah? Capillaries are delivering CO2 into the alveoli, and the alveoli, I can't do English, are delivering oxygen to the bloodstream, obviously. And you know that already. You don't even need to do a test or a tutorial to figure that out because you've been living that your whole life. Okay. All righty. So there's just an extra, can you pop yourself on mute if you're not talking, just because there's some quite enthusiastic children and stuff in the background, which is fine. I've got one too, but I told him to shut up. Okay, so a little bit of extra there. That's just to show you what's going on. All right, so obviously oxygen and carbon dioxide moving into the alveoli, oxygen moving out of the alveoli and into the blood, because that's the whole point. You need oxygenated blood to get around. Okay, on the right-hand side as well, there's another infographic. I've just put tons in, but hopefully so far we've got this CO2 from blue blood into alveoli, O2 out into red blood, making it red blood. Yep. Because then it can attach itself to all the hemoglobin, become oxyhemoglobin, travel around the body and make everybody happy. Okay. Oh, now this one's a nice tricky one. Now you've got to know your regions of the brainstem. Describe how brainstem centers control breathing. Which brainstem centers are we talking about for starters? Where's our main one?
So from the medulla, do you mean?
Yep, absolutely. Yep. So medulla oblongata is one, controlling breathing. Yes. Does anybody else want to jump in with a more detail or extra detail?
Do you mean like the neurons, like in the medulla? Yep. Tell the brain to, does it like contract the diaphragm? Is
yes,
that right?
Absolutely, yeah. Absolutely. There's a number of them. So let's have a look together. But you're right. Okay, so all regulated by cerebrain, obviously, and we're talking about the medulla oblongata. But basically, the thing you want to, if you had that in an exam, it was describing, you want to talk about these two different nerve signals that are sent. Yeah, so you've got, as you can see out there, you don't need to remember things like the pneumotaxic center and the apneustic center, unless you really love Latin and those words actually mean something to you. But just have a look down. So in the medulla itself, there's a ventral respiratory group of cell bodies of neurons, and there's a dorsal respiratory group, and they go to different places. Yeah, so it's pretty important to remember what's going on there. So your ventral respiratory group is going to all of the accessory respiratory muscles. So that's, for instance, the intercostals between your ribs, and the dorsal group are going to the larger muscles on the outside. Okay, so all of the different things you're actually wrapping around the actual rib cage itself. So it's really important to remember that there's those two different nerve pathways, but as long as you can remember, like for instance down the bottom, the medulla tells the respiratory muscles to contract by sending action potentials down two separate nerves. If you can remember that it's the dorsal and the ventral respiratory nerve, that's fine. If you can't, just remember that we've got to have all of that from the medulla down two different nerve pathways. Okay, very important actually, that one. Okay. Okay, this is an explain. So this is one where we've got to tell stories and get ourselves all excited about gas exchange, partial pressure of gases, how carbon dioxide is loaded in the alveoli and how it is unloaded at the tissues. So my question to start with is not just throw the big question at you, but where would you start with this? What do we need to talk about? Because the pertinent word here is how. So it's not just, we know, we've got the fact, we know that carbon dioxide is loaded in the alveoli and it's unloaded at the tissues, which should be in the from to the alveoli and from the tissues. I think unloaded from the tissues as opposed to at the tissues. Anyway, that's just me being a little bit persnickety. Okay, so the question is how. So what do we need to talk about?
Circulatory system.
Sorry, we need to talk about
The circulatory system that the blood comes to the.
Dead set, because do you remember what that's called when the ventilation perfusion? Yeah, so it doesn't matter if you've got all the air in the world in your lungs, if the blood's not getting there, there's no exchange happening, is there? So absolutely, yep, blood supply is really, really important. So if there's some kind of clot, some kind of blockage, and blood is not getting to the alveolar capillary beds, then we're not getting any gas exchange. And this happens all the time. Okay, what else do we need to talk about with carbon and oxygen loading and unloading?
The capillaries.
Yes, absolutely. And do we need to mention things like diffusion? Simple diffusion would be a term you want to chuck in there. Yep.
How they're transported across.
How they're transported across. Good.
And back.
And back. Absolutely. Yep. And indeed, absolutely. But so the question was specifically carbon dioxide. So it's fairly simple in terms of the alveoli, isn't it? Because it really is just a matter of pressure difference and concentration different, partial pressure of the gases and concentration. Right?
Oh, gradients?
And pressure gradients, exactly. But when it comes to actually how carbon dioxide is transported in the blood, we really do have to mention the bicarbonate ion and the fact that it actually dissociates. Yeah, because oxygen is pretty simple. Oxygen is just attached to hemoglobin. It becomes oxyhemoglobin. That's it. It's not as simple with carbon dioxide, right? It does come from the tissues as CO2, but then because we're watery buggers, CO2 and water equals carbonic acid. Carbonic acid is a stupid, weak molecule that just like falls apart at the drop of the hat, and it does, and becomes a bicarbonate ion and free hydrogen ions. So it's really important to mention that in terms of carbon dioxide transport in the blood. Okay. Very important. And in fact, that's one of the things that our chemoreceptors in the carotid are so good at, is figuring out how many hydrogen ions we've got and whether or not we need to adjust things, whether the blood pH is changing unfavorably. So that was the stuff we talked about last week with different chemoreceptors in the carotid and the aorta. Okay. Now, what else have I put in there? I haven't. I've just gone straight to this next thing. So again, yeah, just make sure a lot of this, in terms of answering exams, it's just remember all those key words and phrases and get them down in dot point and let them kick off the rest of your thought process. But it's going, okay, what do I need to talk about this, and this, and then I'll be all over it. And that's fine. And even if you can't talk about it, at least you've listed it, which means you've got half marks already. Right.
So Catherine, would you also mention, sorry, I couldn't talk before because my daughter was having a meltdown in the background and still
That's
is.
All right. That's okay.
House is full of COVID. It's fun time here at the moment.
Oh, good. Yep.
Yeah. So are you talking, so when you were talking about that, so would you mention too about it releasing the hydrogen to change that pH, like that can change the pH and things? Is that what you meant as well in that question, or not so much?
I think you're only talking about transport. So I think if you jumped that further step and started talking about chemoreceptors and hydrogen ions and acidity, we might be jumping a little bit too far. Okay. Yeah, you only really need to talk about the fact that it's CO2 and water means carbonic acid, means breakdown, means hydrogen ions free in the blood. And that would be that stop there. Yeah. Okay. Now, again, this is a drawing exercise, and technology hasn't yet caught up with us having this on a perfect whiteboard so everybody can draw something together online. That'd be nice. In fact, it probably exists. It's just that I don't know how to do it, so someone can tell me if they do. But either way, this is a sort of handy little 4-step drawing exercise for filtration and osmotic pressure. And I do recommend that you don't only answer the questions, but that you do actually kind of draw it out for yourself and use colors. It makes a big difference to learning when you can actually see it and you've drawn it out. Okay, so I've popped all the answers on the right hand side, of course, because that's what we do. But is anything in there unclear to anybody, or is that reasonable? We're talking about, well, actually, does someone want to give me like a working definition of osmotic pressure? What do we mean by osmotic pressure?
Like the tendency of water to move across a membrane to balance the concentrations?
Yes, perfect. And I'm so glad you said it like that, because it was sort of sciencey, but not too sciencey. It's good. Yeah. So osmosis, not like diffusion, from an area of low concentration to an area of high concentration, isn't it? Because the water's mission is to go dilute the stuff. Yep. Okay. So osmotic pressure is talking about how much stuff is in blood compared to how much stuff is in whatever space that blood happens to be going in. In this case, we're talking about, obviously, the alveoli. So we just got to figure out where things are moving and why. So capillary pressure is higher, pushes fluid and oxygen molecules through the wall and into the surrounding tissue. Yep, and that's called filtration. As the blood moves towards the venous end, because we've just pushed crap out, not crap, good stuff, we've pushed stuff out, obviously the blood pressure inside that venous capillary is going to fall because we've just pushed out lots and lots of water. Okay, so the pressure is going to fall. There's a whole lot less in there. Okay, this allows the proteins in the blood, so this is pretty important, to exert what we call colloid, which simply really means proteins, osmotic pressure, in which the albumin pulls albumin in the blood pulls water and CO2 back into the capillaries. Okay, so it's, although there is less pressure inside the capillary at the venous end, what we end up with is a whole lot less water and a whole lot more sort of, if you want, they're not clumped, but concentrated proteins like albumin in what's left, right? And those proteins are going to pull water and carbon dioxide into that capillary again. Does that make any sense? Sort of? Okay.
Yeah, it does. With with osmosis and stuff, like with the water.
Yep.
Could you just explain, I don't know if this is going to sound really silly.
No, it probably, look, it could, but I'm still going to answer it because it's probably like a question that everybody's got. So, yeah.
So when you say, we're like, was it emotional cucumbers and like water in the body and, stuff like that.
Yeah.
When I picture the body, like it's just blood, I think of, like, where's the water? Like, is it just like in the blood?
Well, mostly in the blood and interstitial fluid. So if you think about blood is actually like 90% water.
Oh, right.
Yeah.
I've probably got that written in my notes somewhere, but like.
Yeah. So there's an enormous amount, like with this is basically, we are, even when you spin your blood down in the centrifuge, you've got this tiny little bit of packed red blood cells.
Yeah.
But then it's all plasma, and plasma is all water with a few dissolved solutes.
Okay.
Yeah, there is also some fluid in interstitial spaces between tissues, but obviously very, very small amount. Vast majority of the fluid in your body is blood, and then there are some other, fluid aspects as well. You can imagine like bile, lymph,
Yeah.
interstitial fluid, although we don't want too much of that. Tiny little bit, please. Thank you very much.
Yeah.
Yes, Amy.
I have a question too, which I feel like I don't really know how to ask, and it's
Sure.
probably stupid, but
No, just
What
you know
I
what,
want-
stumble your way through it. We'll get there.
so there isn't actually like blood, like as in red blood cells in the tissues then, is there? Like, because that's not what's going through the capillaries.
Yeah, no.
Yeah. So it's
Yeah.
just the stuff that the blood's carrying.
Yeah, that's right. Exactly. And that's not a stupid question at all, because it's about all of anatomy and physiology is really about compartmentalizing where stuff actually is. And you go, if you cut into a tissue, and this is just logical, right? If I cut into my arm, I'm going to bleed, right? But what I'm doing is cutting through blood vessels. The tissues themselves are literally just sheets of cells, aren't they? Depending on what tissue they are, but they're sheets of active cells with nucleuses and mitochondria and all the rest of it. There's no red blood cells involved in that though. But all those tissues are fed by millions and millions and millions of capillary networks, right? Which are constantly exchanging oxygen and nutrients and making sure that those cells have what they need to actually exist and metabolize and do what they need to do, divide, what have you. Does that make sense, Amy?
Yeah, kind of. Yeah.
Yeah.
So like if you cut your top of your finger, like
Yeah.
a paper cut or whatever.
Yeah.
That like
Do you want
what's that?
me to get gross on? So if you
Why not?
cut the top of your finger and you washed it out beautifully, and then you tourniquet the end of it, right? So there was no blood flow to the rest of the finger at all. Obviously, this is one of the reasons a tourniquet works. It stops the blood flow, stops the bleeding. And then if you wanted to get really gross, you could just open up the top of your finger, like get a scalpel and just open it up. And all you would see is layers and layers and layers of tissue, but the capillaries themselves wouldn't be infused because you've cut off the blood supply.
Yeah.
Does that make sense? Yeah. So it wouldn't be bloody. It'd be, pinkish white, but it wouldn't actually be bloody or bleeding anymore if you cut that supply off. So yeah, red blood cells, all that stuff, it only exists in the bloodstream. And you know what that looks like? The venous network, the capillary network, the arterial network, you know what that all looks like, right? It gets smaller and smaller and smaller and goes everywhere. But that's its job, is to feed those tissue cells. And it's exactly the same thing we're talking about before with, carbon dioxide and oxygen loading and unloading. It's only two of the substances that we are loading and unloading.
Mm.
Yeah, we're also feeding cells everything else, glucose and electrolytes and minerals and all sorts of things.
Yeah.
Yeah.
So just like on a smaller scale, like say you get a paper cut and it bleeds,
Yep.
and it's red. Is
Yep.
that so? Is what you've cut other than your skin, like, is it the capillary that's
Yep.
blood vessel that's bleeding?
Yep.
Yeah.
Absolutely. Yep. So you've literally compromised the walls of, arterial or venous capillaries. It's very difficult to tell at the capillary end. Like you can't cut yourself and go, oh, luckily I missed the artery. They're so small that it all looks the same at that particular point. It's only when you get into the bigger vessels that you can really tell, like a venous cut is just slow and pulsing and oozy. And an arterial cut, obviously we've seen the movies, huge pressure and walls are painted and stuff. Does that sort of answer your question, Amy?
Yeah, it does. The other thing I was wondering was, when they take blood from your blood test, like as a blood test,
Yep.
and it comes out of your veins.
Yep. I
was, again, not sure how to explain what I'm saying, but like that's where they test your levels of stuff.
Yep.
But isn't that? But then we've sort of learnt that like your glucose and stuff in your blood's already been dropped off in the.
No, so the reason that they take venous blood for testing is because it's a cycle, the capillary bed. Right, so if you think of the arterial side of it coming through with all the amazing nutrients and what have you that whatever those particular cells are need. So we have a massive unloading, first of all, right, of oxygen and nutrients. But then as soon as the cells have what they need, then whatever's not used is loaded back into the venous supply.
Yeah.
Yep.
Okay.
So it gives you an idea. It gives you an idea about half of the body, but it's very indicative of where the levels are healthy or unhealthy. So it's based on the parameters of venous blood. So we know that it's not going to have as much oxygen as arterial blood, but we also know what those levels of oxygen should look like in venous blood. And that's what we're looking for. Is it that level, or is it something different from that level?
Yeah.
Yeah. Does that make sense?
Yeah, no, that makes sense. Thank you.
Yeah, cool. It's also the other reason is practically the reason that had to happen. The reason it evolved like that is because if you stick a needle into an artery, it's not very useful, and also tends to gush everywhere, and it's not very controlled. Venous blood is lovely and slow at very low pressure, right? Can be drawn by a needle very easily. Arterial blood, the stopper would fly off the end. I'm being overly dramatic, but that's basically why we do it. Yeah. Okay. Cool. All right. No worries. So, I'll leave you guys to draw that in your own good time, I think. Okay. So to finish us off, and I know I've gone really fast too, but I'll leave heaps of time at the end so people can ask me questions, stupid or not. There's no such thing. I think they're all really interesting questions, actually. Okay. A member of the Blues Gang. I don't even know why the Blues Gang, but anyway, maybe she was thinking Blues Brothers when she wrote the slides. I don't know. Rushed into emergency room after receiving a knife wound because, I don't know, Mac the knife was in town, in the left side of his thorax, and the diagnosis was a pneumothorax and a collapsed lung. Explain why that the lung collapsed, and also research the term pneumothorax right now. Immediately. However, we will research the term pneumothorax together, but can anyone explain to me why that knife wound caused a collapsed lung? What did it pierce and why is it important?
So the knife has actually pierced the lung. So it's gone into the space that's between the lung and the lung wall, into the pleural space.
Yes.
Which is filling up with air, which is creating pressure on the lung and making it shrink, so there's not as much airflow going into it.
Yep, absolutely. So, and why is it that when that fills up with air, what's happening to the pressure? What is the lung used to? What's the pleural space normally provide? Is it positive or negative pressure?
It's usually negative pressure.
That's right.
Yep.
Yes. Be confident. Be confident. You had it. Yes, it is negative pressure, but that is it's the partial pressure difference between that pleural space, the interpleural space, and the lung itself that keeps them expanded. Yep. So the second you pierce it, you're right, air rushes in. All of a sudden, it is not negative space. It is now positive space, and the lung cannot support itself in that space and collapses. Good. All right. That's exactly right. Perfect textbook answer. You should trust yourself, Alison, because you're so right. Okay. So, as we said, differences in pressure is really, really important. Intrapleural pressure. So try and remember, guys, that if there's three things you need to know about the whole respiratory system: intrapleural pressure, alveolar pressure, and atmospheric pressure. And it's the dance between all those three types of pressure that is why we breathe in the first place. You may think it's got to do with your will, that you want to breathe. Actually, it's got nothing to do with it. It's the atmosphere trying to get in and blow you up, but you have mechanisms to stop that. Okay, so you also have to remember atmospheric pressure. So hopefully you can remember 760 milligrams of mercury. That would be good. Okay, so now pneumothorax. Is anyone able to quickly look up a definition of the good old pneumothorax?
Does it just mean collapsed lung?
Yeah, pretty much. Yep. Okay. Pneumothorax, collapsed lung, but it's the proper term. So you've got to use it, right? Because, you know, when you're working, that's exactly what they'll say. They won't say collapsed lung. They'll say pneumothorax. And you go, I see. Was the pleural cavity compromised? And they'll go, yes. You go, I learned that. Good. So exactly that. So usually, and the important bit about this pneumothorax thing is that it can come from all sorts of different possible things. So yeah, it could come from a stab wound. Most of the time it doesn't though. Stab wounds aren't as common as we've been led to believe in our movie history. Same as we all grew up thinking that Bermuda Triangle was like, I don't know what went on with that. It stopped working. Nothing's happened there for like at least 2 decades. I don't know what happened. Anyway, so it can be any kind of chest injury at all. So this can be, you know, from football. This can be from, you know, underlying disease like COPD or chronic asthma. It can happen all over the place for no apparent reason. So it doesn't require a knife every single time. Any compromised pressure at all. Someone think of another reason that the pleural space might be compromised.
Cystic fibrosis.
Yep, cystic fibrosis, absolutely. What else?
If like air pushes out of your diaphragm?
No, because diaphragm's a muscle.
Right.
Yeah. Oh, but good to say. I'm glad you said it because here we go. This is a little tiny bit of story time. So if you've ever been to anybody that purports to be a breathing expert, they will often say, breathe with your diaphragm. Or even worse, breathe into your diaphragm. Now, you can't. It's a muscle. It doesn't have alveoli. It doesn't have air sacs. It is literally a muscle. And its job is to change the pressure in the lungs. Okay? So when it goes down, the muscle pulls down, you're changing the pressure in the thoracic cavity. When it pulls up again and in relaxed state, it kind of looks like an upside down kidney, then that's changing the pressure in the lungs again. You cannot breathe into your diaphragm. You cannot breathe with your diaphragm. It's autonomic. It's like something you actually can't control. Having said that, you can control it over a period of time with a lot of work. So this is, think monks and opera singers and things like that. You can, with a lot of very deep breathing and a lot of controlled exhalation, you can control the rate at which your diaphragm lowers and rises. Yeah, but long periods of practice. This is not something you can decide to do tonight, so don't try. Yes, Steph.
I've got a quick little story that I don't know, maybe you might be able to shed some light on.
Oh, on a story. Good. Yep.
Yeah. When my sister was in labour, I'm not sure if anyone else has had this happen, but no one else had heard of it, like where, you know, professionals had really heard of it during labour. But she ended up with subcutaneous emphysema, where the air had pushed out from somewhere. Like, I don't know, I thought the diaphragm, that's why I said that before.
Yeah.
And then she ended up with like her skin was like bubble wrap because like air had pushed out from somewhere, and then underneath her skin for the next few days, it was like bubble wrap because she had air floating under her skin.
Wow.
Something like that. Yeah.
Wow.
And it just
all I can think of there is massive pressure in capillary beds or venous beds, and I'm not sure, I can't figure out how it would get there. This is probably why the experts that were in attendance were a bit kind of, sorry?
Yeah.
You just broke science. What? Like, I'm going to look it up though. That's really, I can't tell you the mechanism. But excess air under the skin.
Yeah, I don't know. Yeah, that's how they so like a few days, like, so the next couple of days she ended up with shortness of breath, and they didn't know why, and they did an x-ray, and that's what they found.
There was no explanation for how that air got to, because it shouldn't. There shouldn't be any way for air to get there at all, because like blood doesn't carry air, blood carries oxygen. but doesn't carry air. Air only goes in and out of lungs. So the
Right.
question about this is how did, like, the lungs are a closed system, you know, how did the air get from the lungs to
Yeah.
under the skin?
Yeah.
I'm so looking it up.
So-
Thank you
yeah.
for my little piece of research though there, Steph.
Yeah.
That's
That's right.
fascinating.
Yeah, it
And
was like bubble wrap.
did it resolve itself? I
It
assume
did.
so.
Yeah, but it just
Okay.
had to resolve itself. Yeah.
Wow. Yeah,
Like
I
a
wouldn't
fix.
even know what to do with that, like in a clinical situation. But I think you should lie down. But
Yeah.
other than that, can we shut it down? Can we put her on a ventilator or something? Because it's scary.
Yeah.
No idea, but I will look it up and see if I can find you a decent answer at some point.
Okay.
But thank you for the story though. I think I love medical mysteries. I think they're wonderful. And I don't know the answer, so I'm going to look it up. That's awesome. All right. Now, thank you. Is there? Let's see. Oh, sorry. There's people. That's okay. People have said, Jody, partial lung collapse from pneumonia. Yep. Okay, because that's another one that's huge is pneumonia, and you've got to be really careful of that because that's the pleural cavity that is infected. And obviously, if you've got any change in pressure from bacterial overload or anything of the kind, then pneumonia is, you know, not going to necessarily, but could lead to a collapsed lung very, very easily. Yes, Amy.
Oh, sorry, just another question.
Yeah.
Because I wrote this down as I was going through the slide and I didn't really get it. And then I thought, well, what's the point of writing it down? So at the end of the last slide, it had a clinical application about pulse oximeter, however you say it, oximeter?
Yeah, oximeter. Yep.
Oximeter, yep.
Yep.
And from what I remember last year in the clinical reasoning, the ideal reading for that was between 95 and 100%.
Yep.
And then on the other side of that slide, it had about the partial pressure. It's sort of indicating about how much percentage of hemoglobin is saturated with oxygen.
Yep.
And it said on there at rest, partial pressure of 40 millimeter mercury.
Yep.
Oxygen, there's about 75% of hemoglobin saturated with oxygen. And then I was a bit confused by that because I thought sort of under 90% you were, you know, not doing well at all.
Yeah, okay. So this is talking about the difference between what the pulse oximeter is measuring and what is actually going on in the blood. So again, it's sort of indicative rather than anything. So when you're how do I describe it properly? Because it's the numbers that you're crunching and they're not crunching, right?
Yeah.
Yeah. Okay, good. How do I describe? Sorry, I'm tired too, Amy. I'm just trying to think of an easy way to put that. But basically the pulse oximeter is measuring a blood value, but it's not measuring the actual percentage per se. I don't know if that makes any sense. It's so if the pulse oximeter says 75, that's not 75% oxygen.
Yeah.
No, it's 75% loading
Yeah.
of the hemoglobin. Does that make sense? So it's still 75% loaded. Just means that
it's measuring in where you've put the thing. Yeah.
Yeah. Yeah, exactly. So it's that could mean that overall your blood oxygen levels are well and truly at 90 where they should be.
Yeah.
Yeah, but it just means that, so what it's telling us is how is the hemoglobin working? Is this working? Is it picking up? Is it being fully loaded each time there's a cycle, or is it not? And if it is not, then we need to do some further investigation, because it's, you know, is it that there is a hemoglobin molecular structure problem? Is there possibly not enough iron, right? If there's no iron sitting in those particular areas, the hemoglobin molecule, it's not going to pick up the oxygen that it needs to pick up either. And this often happens in anemia. Yeah. So it's saying 75% of the hemoglobin is being used, not 100.
Yeah. Okay. Yeah.
Yeah.
No, that makes sense. Yeah.
Cool. Good.
I just-
I get the question 'cause it's like, yeah, what? None of these numbers match. What? Can we talk in plain maths where they do match? Yeah, they often don't. But it's often got to do with, you know, the parameters that particular instrument is measuring and how they're measuring it as well. Yeah. All good though. Good question. Very good question. And it had me thinking for a second. I was like, how do I do it? How do I explain it? It's good. Thank you for the exercise. All right. Now, are there any great problems with that whole respiratory thing? It's mostly pretty straightforward. Is there anything that people are struggling with particularly? Of course, the answer is I'm not going to be able to magically help you not struggle right this second. But at least if you can identify areas that are a little bit shaky, that's what you need to go read more on and listen to more on. If you can find, you know, YouTube stuff that explains it for you, that's brilliant too.
Sorry, after the class, am I able to just talk to you for a quick minute?
You are able to talk to me for a quick minute, as long as everyone else promises they'll sort off. And then I can keep the room open, and I'll stop recording as well so that it's not recorded for every other student and posterity as well. Okay, well, Maddie, yes.
Sorry, this isn't to do with me, but a few people have mentioned and asked if we could ask you tonight that in the mini test 3, one of the questions didn't get marked, the spinal cord question. So they're saying they got their results back, but one of their questions weren't marked. So they just asked if we could raise that with you tonight.
Yes, you said, sorry, I'm reaching for a pen. I'm not running away. So I was like, I'm just going to leave. Because it's not my responsibility. No, I'm just writing it down so I don't forget tomorrow. So mini test 3, and it was.
Has it already been marked?
I don't
Like,
think they're meant to have been
released?
released yet. So that's probably why. Yeah.
Wait, what was that? Sorry.
I don't think they're meant to have been released because it's only been 5 days and they've got 15.
Yeah, you know what's weird about that? That's actually, I heard that from the internals today too, where people's
it got released.
the occasional mark has been out, but not everyone's got it, is what I'm hearing.
I got mine.
You got yours?
Yeah, I
I
got
got
mine
mine.
today too.
Okay, well
got
that
mine the other
sounds
day.
like they've released it. Okay, but
But
so
I
sorry.
have mine, like, so there's some
yeah,
people
I
who
just-
don't.
I just looked at mine and it doesn't have a mark, but when I click on it, I can see they're all marked but one.
So which question is it? Sorry, Maddie or Nat?
Yeah, so the question, it says needs grading is describe the major function of the spinal cord in the simplest way.
Yeah, that's the one that everybody's saying got missed with
So
marking.
because that one's not marked, I don't have a grade overall
Yes.
yet. But
Well,
when I
you
click on it, I
shouldn't.
can see the others are marked.
If it's not completed, you shouldn't actually be able to go in and see it yet anyway. So I'd say
Yeah.
I will take that to Nat and see what's happening. I'd say somebody, possibly it may be an IT issue, it may be a marker issue where they're not sure which button to click. It could be that simple in terms of just the admin side of it, not the knowledge side of it, but the am I supposed to hit release here or not release? Or it is a complex system, I promise. But I'll follow it up for you and I'll pop an answer on the discussion board as soon as I know.
Thank you. I'll let them know. Thank you so much.
Yeah, you're welcome. All good. All right. Well, if you would like to run off now and have your din-dins, please do that.
Catherine, I've got to head off. I've
Yes.
got a P&F meeting to go to.
Oh, yeah.
Yeah, but I just want to say thank you so much for this session. I've really enjoyed our tutes. And
Oh, thank you.
yeah, hopefully I'll see you along the line.
I
yeah,
think you'll
future.
guarantee you. I think I'm 175ing you guys as well. So
Yeah.
I suspect I'll be leading you through all of that as well.
Yeah.
Thanks
So
for
hopefully I'll see you
everything,
next
Catherine.
session.
Yeah,
All
and I
good,
really
guys.
hope, I hope my confidence builds, like getting through this session. I hope,
It will.
So
It will.
seeing
Unless,
myself as an RN after I get the, physiology and anatomy stuff done.
You will. And don't be too rough on yourself. Like it's a lot. It's a heavy amount of information to take in. Most of it won't sink in properly until like 2 or 3 years out of uni. And you'll be exposed to it every day. And you go, see, now I know the partial pressure thing, but it was vague when I was studying it. And that's a fact. It's true for everybody. Yeah. So don't worry about it. I think you're all doing brilliantly. And every single Monday, you're caning through all of the questions. Everybody's got an answer ready to go. You're all doing really well as far as I can see. So hopefully your marks are showing the same kind of trajectory. I'm not going to ask you to admit this though, like in public, but if not, you'll be fine. And we'll, it's only first half. We've got to still get through 175. So let's all stay very positive, shall we?
All right,
guys.
See you guys.
Catherine, I did some research on my husband's pacemaker with being under the rib cage.
Yeah.
From his professor, his
Yeah.
doctor. It says it's part of his heart repair, and one of the complications he's had was a main blood vessel on the top of the heart to the body. The SVC is blocked.
Ah.
And
Okay.
normally a pacemaker is out in through the SVC, so that couldn't be done. So as it was blocked already, that's why it's under the rib cage.
That's so logical. That should have been something I landed on straight away. It's like there must be something wrong with the original vessel, but also didn't want to go there too much and say, I think your husband's heart's blocked, because that would. But yeah, that makes perfect sense. That's awesome.
Yeah, because he was born with the arteries be burst for the body.
What a silly! Tell him to stop that rubbish. Well, that's just ridiculous.
So he had an operation when he was 18 months old to repair it, and then a pacemaker later on.
Wow,
So-
typical men though, but just not concentrating
Exactly.
in the womb, and you got it backwards. Like,
Yeah.
sorry,
Jody.
I'm being terrible.
Jody, what?
Yeah.
Sorry, what did you say your husband had? I missed the first bit.
The pacemaker is under the rib cage.
But what did you say about his heart?
He was born with the arteries going the wrong way. So the one that normally carries the blood to the whole body was traveling to the lungs and vice versa.
Transposition of the great arteries?
Exactly.
My daughter was born with the exact same thing. She had to be operated on though at 7 days old.
Yeah, well,
Jody.
Yeah, well, my husband, he's coming up to 46 next month.
Yep.
And at that time, they weren't doing surgery until 2 years old.
Wow.
So they did his at 18 months. And he was one of the first ones to be done at Melbourne Children's Hospital.
Wow.
Yep.
At that time. And then later on, he's now got a pacemaker. But it was put underneath because the SVC was blocked.
But that's
So
good though,
it's
Jody.
like
At least.
Yeah, well, we sent it off to his professor that looks after his heart at RPA to find out the other day, because even his parents didn't know why at 18 he'd been put under. And I mean, he's 46 and he's still got pacemaker now.
Yeah.
But
good
that's
news.
a real small world, Jody.
Wait that long because my daughter had to be operated on quickly. Otherwise, she would have.
My question
died.
is, how did he get to 18 months?
Yeah.
Like, that's amazing.
Yeah, they said he
they
was
said-
classed as a blue baby.
Yeah.
Yes.
And
Yep,
he was
absolutely.
growing too fast. So they were trying to keep him until he was 2 years old because that was what they knew then. So it was
That's-
a real,
it's
but now it's done
extraordinary.
really quickly. But he's coming up to 46.
Yeah, cool.
Too,
My daughter's only
so-
8, but so far she's doing really well too.
Yeah, well,
Jeez.
he couldn't wake up. His parents were having trouble with him waking up when he was 18, and his heart rate was dropping below 40 beats
Wow.
at night time. So the heart pacemaker kicks it in.
Yeah,
So
cool.
it gets a little scary.
Yeah. Well, yeah. I'm
It's
but I'm
amazing how
loving-
much technology's come along.
Medicine's come along. I was saying to my internal class today that in the 70s, when some of us were born, if you had tonsils that got infected, they just ripped them out. So no, hardly anybody of my age has tonsils at all.
Yeah.
And everybody does now because they sort of realised a little bit later on that they're quite important in the whole lymphatic system. So yeah, I don't know, medicine does leaps and bounds.
Where it is. I have this at the moment. I don't know. Going to show it.
Oh, yeah, I can see that.
You see where his pacemaker is?
Yeah.
It's down in the abdomen.
Thanks for
It's not
showing
up
us
the
that.
top. He just had a chest X-ray done, so it's just interesting.
Yeah,
how they've
it's
done
really
it.
interesting. Thank you, Jodie's husband. You're awesome. Thank you.
Oh,
All right,
it's
guys.
good. It's interesting. Even his parents didn't know why it had been done.
Well,
And his
see,
professor
aren't they
turned
lucky
around
that
and said-
you're studying nursing and that you're out there like this little Scully investigating the everythings and finding all the answers?
But it's
It's awesome.
amazing though
It is. And also
how
he's
things
there.
have come along. Yeah,
Yeah.
he's here.
Yeah, which is a good
The
thing.
only complication he got from having that surgery that later on was that because he was under for so long, he ended up becoming epileptic.
Oh, okay. But that's at
So
least something
at-
you can manage. That's
Well, at 16, he had part of the frontal lobe removed to help with the seizures. So yeah, he's a bionic man.
yeah. And like that's it. He's a book. Like he's just a book of medical marvels, basically. He's exciting.
Mhm.
Yeah, he's like a Rubik's Cube with all the colours in the wrong place. It's
Yeah,
that's awesome.
But it's great now, Jodie, that they do it so early on.
Yeah, absolutely. And all the things you
well,
guys have been
that's right.
through too.
They told me later on, the valve, I forgot that you're born in your heart and it closes off after a certain amount of time. I think it's within 24 hours.
Yep.
And we didn't know that she had TGA. It was just that, yeah, she was blue, she wasn't waking up, blah, blah, blah. Yeah, they said if we didn't pick it up when she did, so she was like 14 hours old when they finally were like, oh, something's wrong. Yeah, she would have died later on that night because that little flappy thing was the only way she was getting like the tiniest little bit of oxygen actually to her brain. Yeah.
Whew.
Yeah.
All right.
And it was her being in hospital, like, because we were in the ICU with her in Sydney for a month. It was that, and although it was 8 years ago, that got me really intrigued in nursing, like watching those ICU nurses. And I was like really nosy at like why all the other kids are in there. Yeah, it was that actually made me want to do this.
Do you know, I often find that,
like I said,
particularly
it's only taken me 8 years to actually sign up.
But with distance students, I always find this really interesting stories about things that they've seen or been through or whatever. And there's always some brilliant story behind why I decided to do this. And it's also why you guys, sorry, I shouldn't say this, but beat everybody out of the ballpark when it comes to marks every single time, because you guys have you've got a fire. It's not just something you're doing to fill in time. You know, you're doing it for a reason and you bloody know it.
Yeah.
And it's great. Anyway, everyone has to start off now except for Chloe, because I have to also have my dinner and a getaway. So I'll see you probably next session. Yep. All right. Thanks, guys. Go away. Right. Let me stop recording.